So for the STM part, the robot utilizes the gyroscope and PID on board of the STM for its precision, allowing it to turn to any required angle and thus safely navigating through multiple obstacles. The ultrasonic sensors are also used to avoid collision with obstacles in front of the robot by stopping the robot once an obstacle is detected within a defined range. For the second task, our robot relied on the IR sensors to identify the start and end position of obstacles by tracking the linear displacement of the encoder values. This ensured that the robot would not turn too early or too late. And lastly, a set of standardized commands were implemented to allow easy communication between RPi and STM.
To determine the most efficient route for our robot, we implemented the A-star search algorithm to compute the fastest Hamiltonian path. In our setup, each node represents a key location just before an obstacle, which serves as a critical waypoint the robot must navigate through to successfully traverse the environment. The algorithm evaluates paths by combining the actual course, which is the distance already traveled, with a heuristic estimate of the remaining distance to the goal. This allows it to prioritize routes that are both promising and efficient, minimizing unnecessary exploration. What adds flexibility to our approach is the robot's ability to move in both forward and backward directions along the grid. This bidirectional movement enhances maneuverability in tight spaces and contributes to a noticeable reduction in the total time required to compute the path.
I am Jun Jiang, the developer of the Android app. After the app is connected to the robot, user can place obstacles and robot into the map. User can set the direction of the obstacles that the robot should scan on, set the direction of the robot, and remove them by dragging them off the map. After setting up the map, user can send the map setting to the robot and start task 1 and task 2 by pressing the button at the side. The app is also able to control the robot's movement, send commands, and receive feedbacks.
The Raspberry Pi with an attached Pi camera connects to an Android device via Bluetooth to receive obstacle coordinates. It then transmits these coordinates to an algorithm server on a laptop over Wi-Fi. Based on the algorithm server's optimal path calculations, the RPi sends movements instructions to the STM via USB. Acting as a system's brain, the RPi ensures efficient communication across all components.
For multi-programming, we have considered 3 approaches: team-up sessions with separate Python file coupled with local WebSockets, Python multiprocessing library, and C multithreading library. We ultimately selected Python multiprocessing library because we are on a full-core Raspberry Pi. Each Python process will have their own interpreter and memory space, so it will be able to bypass the Python GIL limitation. For image recognitions, we have selected a pre-trained YOLO V8 model to fine-tune with 12,000 label images. The training is conducted on A100 GPU. When selecting the batch size, we ensure that it's based on GPU memory utilization for each forward pass to prevent the CUDA out-of-memory error. Early stopping has also been implemented to prevent overfitting.